All right, so we'll continue from where we left off at the end of the last segment. And where we left off is what appears on the slide here. Okay, we were talking about the partition of the boundary. To proceed, we go back to the balance law that we wrote out in integral form. And at this point, here's how it looks. So we start out with rate of change with respect to time of the total number of particles here, c d little v, equals integral over omega of the source term, which tells us how many particles are being supplied per unit time per unit volume, minus integral over the entire boundary of our unit outward normal flux. Okay, d little a. Okay, so we're going to proceed like we've done before, which is to attempt to convert these integrals into a single integral over the volume. Now, in the past, when we were doing this in the context of mechanics, we needed to be a little more careful about how we did this term. Can you recall why we needed to be careful about this term? About how we took the time derivative there? What was special about it? Think about it for a second, or a few more seconds. Okay. What happened was that when we were treating mechanics, we were interested in configurations that were changing. As a result, the domain of integration, which I've labeled here as just omega, was changing, right? We were going from the reference to the current configuration, and those current configurations also were changing with respect to time. And so we had to invoke the Reynolds transport theorem. In this case, the configurations are not changing with respect to time. We talked in the previous segment about how we are not considering mechanics and deformation here. As a result, that time derivative is actually trivial. Okay? The derivative can be pulled into the integral sign without any special treatment. And so we get integral over omega partial time derivative of c. It's a partial time derivative because, remember, in general, c is a function of position and time. Okay? All right. On the right-hand side, we have integral over omega pi, and now I'm going to introduce I'm going to just, in this line, include all the arguments. Okay? And now we have the last term. We do here the divergence theorem. Okay? So here we get minus integral over omega. J is a vector, of course. We get minus integral over omega divergence of J dV. Okay? And I'll mention here that what we've done is we've applied the Gauss divergence theorem. Okay? Applied to J, the flux vector, which is a vector, of course. Right? We've just reminded ourselves that that's a vector. Okay, now things are really easy here, as you can see. And the ease arises from the fact that we are ignoring the change in configuration here. So we get, properly to be consistent, I should write that also as parameterized by x and t. Okay, so we have integral over omega partial of c with respect to time minus pi plus divergence of j d little v equals 0. Okay? And now we will invoke our localization argument. Okay? And that localization argument, if you recall, says that yes, we've written this as an integral over the entire body, but equivalently we could have done it for any subset of the body. Okay? So we have this picture. This is the picture for which we developed this argument, right? Doesn't look particularly like a vector, does it? Okay, we have omega. It's true that we developed these arguments for omega, but as we've done before, we can equally do this for any subset omega tilde. Okay? All right? And so we can say also holds for any omega tilde subset of omega. Okay, this is our localization argument. And if that is the case, right, and of course omega tilde can be as small as we like within omega, right? And if this condition always must hold for any omega tilde subset of omega, it follows that from the localization argument follows that partial of C with respect to time minus pi plus divergence of J equals 0. Okay? And this holds now at any point in omega, right? This holds in omega, but then it also holds for the time interval of interest, because on the left-hand side we do indeed have a time derivative. Okay, so this is a time-dependent problem. So it's omega cross 0 comma t, where as always 0 comma t is our interval, our time interval of interest. All right. Now, so this is our PDE. This is our equation for the balance of mass. Okay. All right. It needs to be supplemented by boundary conditions as well as initial conditions, just as we saw in the context of mechanics, for instance. Okay. So the boundary conditions in this case are the following. We already looked at the boundary conditions, right? So we just re-enumerate them. It is that minus J dot n, right, which is the inward flux, the influx of particles on the boundary, is equal to the specified number of particles per unit time per unit boundary area that we are sending in. Okay, this holds on the flux boundary subset, and on its complement we have C of, if we like, x comma t equals C bar, okay, some controlled concentration which is allowed to change with time. Okay, right, and actually so is this. When we specify these quantities we are controlling on the boundary, we are allowed to change them with respect to time, but we are controlling them over time. Okay, so we have C equals C bar, could be a function of x and t on the concentration boundary. All right. Okay, and we talked about these when we were setting up the integral form of the balance. All right. The other thing we need here is we also need some other condition in order to solve this problem. Can you think of what that is? What other condition do we need to completely specify this problem? We need an initial condition because we have a time derivative here. We have a single time derivative on the concentration, therefore we need one initial condition. And that initial condition is just the initial value of the concentration as a field over the domain of interest. Okay, so that is specified as C over X at time t equals 0 equals, let's denote it as C naught, where the naught has an obvious meaning, as a function of X only. Okay, all right, that's the initial condition. Okay, so this completely specifies our problem, right? What I want to do now is take just a few minutes in this segment to make a small detour. And what I want to do with that detour is to introduce some more nomenclature, or you can look at it as categorization, which is going to help us organize our understanding of boundary conditions.